Okay, in this video I'm going to move on in our solutions for wave equations, and what we're going to do now is the particle in the 2D box, and we're going to solve the Schrodinger equation for particle in a 2D box. So the first thing I'd like to do is discuss the box. So in front of me I've drawn a Cartesian plane like that, and I've drawn a box just here. Alright, so our coordinates are, this corner here is x equals 0, y equals 0. This is x equals a, y is equal to 0, x equals a, y is equal to b, x equals 0, y is equal to b. And just like the infinite potential well, I'm going to say that inside the box the potential energy is equal to 0, and everywhere else the potential energy is infinite. So the first thing we need to do is note that the potential energy of x and y is not equal to a potential energy of x and y and t. Therefore it's time independent potential, and we can use the time independent Schrodinger equation. The next thing we notice, of course, that the time independent Schrodinger equation has a potential energy term. So it looks something like minus h bar squared over 2m psi xx plus v0 psi. In this case, the v0, the potential energy, is equal to 0. So for that reason, we can say that the time independent Schrodinger equation becomes the following: d times psi. So that's the same as saying the Hamiltonian acting on psi, the Hamiltonian acting on psi is equal to E times psi. Alright? Okay, so it's time to move on. So I've proven the time independent Schrodinger equation in a previous video, so look at that if you want to work out how to do that. But in solving the time independent Schrodinger equation, we used a technique called separation of variables. And this is vitally important here too. Okay, and separation of variables is a technique that doesn't always work, and I don't know exactly why it works, but essentially what we say is, in our current wave equation we have psi as a function of both x and y. It's a function of two variables. And separation of variables basically says that we're able to break this up into a product of two functions, each of only one variable. So we'll say it's, I can't remember what I think that's zeta, I think it is. Okay, and we have eta of y. Okay, or you could say x, capital X of x and capital Y of y. It doesn't really matter. The point is here is that we're able to break up our two-dimensional equation into a product of two functions, each only a function of one variable. Alright, so let's go ahead and solve the time-independent Schrodinger equation, assuming separation of variables for the spatial coordinates. So let's just look at the time-independent Schrodinger equation. Okay. Now, what I say is that we're actually extending into, we'll say, two dimension in this case. So minus h bar squared over 2m times del 2 psi del x squared plus del 2 psi del y squared. That's of course going to be equal to E times psi, the energy. So I said again, I'm just going to do it once more, that psi is equal to, I'm going to say, I think this is zeta, I'm not too sure, it doesn't really matter, and like that. Alright, so what we need to do now is get our derivatives. So psi sub xx, the second derivative with respect to x, is equal to this. Okay, you can do that yourself, I'm not going to babysit. Okay, psi sub yy is equal to this. Alright, so what we're going to do is plug both of those values into our Hamiltonian, and as a result we'll get the following. We're going to get outside negative h bar squared over 2m. Inside we're going to have like that. That's going to be equal to the following. Alright, so it's pretty straightforward stuff. The next thing we're going to do is separate out the variables. Alright, so I'm going to put one variable on one side and another variable on another side. So before I do that, I'm just going to make one quick alteration, excuse me. Like that. Alright, and I'm going to take in, excuse me, I'm going to take the negative is still going to be here, like that. Alright, so the next thing we're going to do is use our kind of dummy variable. Our dummy variable this time I'm going to say is k squared. Usually use alpha, so this time k squared is going to be equal to 2me over h bar squared. Alright, so if we apply this, we're going to get the following. We're going to get, and like that. Alright? So that's just pretty straightforward algebra. So next thing I'm going to do is divide across by our wave function here, and we're going to get, as a result of that, we're going to get, let me think now, bear with me for one moment. Okay, yeah, we're going to rearrange this as well. So we're able to rearrange it like this. Where was 1 second now? Like that. Okay, I know that looks a bit mad, but that's pretty straightforward algebra. And as I've said in the past, if you have two functions, each of which are varying, namely this function and this function, and they're equal to each other, that means they're equal to each other for all time. And the only way they're able to stay like that is if they're equal to a constant. So I'm going to say the constant is equal to lambda squared. Well, in actual fact, I'm going to say it's equal to negative lambda squared. And you might say to yourself, first of all, why am I using a negative here? And the answer is, it's just from experience, that sometimes you leave it in equal to a positive lambda squared or a positive lambda or a positive constant, and sometimes you leave it equal to a negative constant. And it's only through experience you'll know which to use and which not to use. So in generally, try one, and if that works, that's grand. If it doesn't work, then you try the negative constant. Now there's a bit more theory to it than that, but in this case we'll use a negative constant. Alright, so bear with me now, and I just clean up my board. And what we had was the following. We had 1 sec now, is equal to alright, so of course we now have two separate functions. This is equal to negative lambda squared, and so is this equal to negative lambda squared. So we separate out those variables, and we're going to get the following. And we're going to get e to squared, or e to double prime, excuse me, like that. Alright, so we need to solve these two. Now if you look, this is going to be a second order linear differential equation with constant coefficients, and this is also going to be a second order linear differential equation with constant coefficients. Something which we know how to solve ad nauseum at this stage, okay? Now if you don't know how to do it, look at my solution for the particle in the infinite potential well, where I went through this in great detail. And if you can't find that, look at my playlist on differential equations, where I show you how to solve a second order linear differential equation with constant coefficients. So look, I won't do the solutions here because we don't need to do that, right? And we're going to find the following. We're going to find that we have one equation here, and this will give us the x component, and then to get the y component, we have to make another substitution. I suppose I'll do this. Okay, I'll do the second part here. Okay, so we have the following equation. When we do a small bit of manipulation, we're going to have the following equation. We're going to have the double, or the second derivative, is equal to the equation, the wave equation itself, lambda squared minus k squared. So I'm going to make this into negative beta squared. Why negative beta squared? Well, because I want to be able to solve this equation quite straightforward. So if I make this into a negative constant, when I bring it across, it will become a positive constant. Okay, so it's I suppose a small bit of a sleight of hand. If you let this to a positive, then when you bring it over, you get a negative, and when you start solving the equation, it becomes basically a pain in the face. So it's really an experience that tells you what to do. So we'll be left with the following equation. That's a beta. And the answer to that then will be as follows. It will be e to y is equal to constant times the cosine of beta times y plus d times the sine of beta times y. Alright, and that's how you solve your your two-dimensional time-independent Schrodinger equation. And we're nearly there, believe it or not, we're doing quite well. The next thing we need to do is to apply our boundary conditions. So I know I've rubbed out the equations there, but if you want you could note those in your copybook. It's no big deal. So our box of course started at 0 and went to x equals a. So if you plug in for the x value here, we're going to find of course that the cosine goes to 1, and as a result a is equal to 0. Because at this point here the wave equation cannot exist, so it must be equal to 0. Actually, look, I'll do this explicitly just for the crack. So at a times the cos of naught plus b times the sine of naught. This is equal to naught, this is equal to 1, and therefore you get, and the whole thing is equal to 0, so as a result a is equal to 0. And 0, you get this. What did I have? Beta times the sine, b times the sine of lambda x, like so. Alright, that's it very explicitly done. And I won't do it that explicitly from now on. So you find of course that a is equal to 0 with one boundary condition. Next we apply x equals a, and we're going to get the following. We're going to get b times the sine of lambda times a is equal to 0. Now of course b cannot be equal to 0. The reason it can't be equal to 0 is because otherwise we'd have no solutions, because it would be 0 for all time. So we know sine is equal to 0 at integer values of n pi. So as a result we're going to get that lambda is equal to n pi over a. Alright? Next, let's apply these to the y dimension, and we're going to get eta b is equal to, and once again it's going to be like c times the cos of b. Okay, c times the cos of b. Let me think there now. Bear with me one moment. Oh, that's sorry. Excuse me. 0. I'll do b in a second. I'm just looking at the wrong part of my notes. Okay, d times the sine of 0. So for the same reason here, c is equal to 0. Alright? Because the whole thing is equal to 0. You cannot have any wave existing at this point, because we know the potential energy function in this case is infinity, and we can't have the particle existing in an infinite potential. The next thing we apply is eta at the position b, and we're going to get that is equal to d times the sine of beta times b. And that's of course equal to 0 again. And for the same reasons as we said before, we're going to find beta is equal to m times pi over b. Now note of course it's m pi and not n pi, because these are two different let's say variables. We have a lambda and a beta, and we need a different set of integers in order to work out their energy values. Alright, so write those down in your copy if you like. I'm just going to put the whole thing together now. Alright, we found a moment ago that we said that we said that the wave equation psi was a function of x and t. Okay, that's the time-independent equation. And we said that was equal to the following: times eta of y. Alright, and we've just found out what each of these are. Both of these are sinusoids. Alright, and we found out that we had psi of x of t is equal to b times the sine of n pi times x over a times d times the sine of m pi y over b, like that. And now look, we don't need to keep track of these constants. B times d, I'm just going to call it a new constant, and I'm going to call it e. So as a result, we can say that the two-dimensional spatial part of your wave equation is equal to a random constant e times the sine of n pi x over a times the sine of m pi times y over b. Alright? And that's your wave equation solved. The next thing we need to do is normalize it. Now what does normalize mean? I'm actually not going to talk about what normalization means. I'll let you do a bit of research yourself there. Basically what we need to do is find out a value for E, such that when the particle, that makes the particle exist somewhere in space. Okay, and that involves a bit of integration. And there are two different ways of doing this. One is involving double integration, and one doesn't. So I'll show you the quick way first, right? The quick way is this, right? We need to normalize the value of the wave function, right? So that means that if we integrate the wave function from negative infinity to positive infinity, and we integrate its complex conjugate times the value itself. And in this case, because we're going two dimensions, we need to integrate dx dy, the value must be equal to 1. And when you do that, you'll get your normalization constant e. Now, there are two ways of doing it. Remember what the wave equation looked like. It was psi is equal to e times a sine times another sine. So you could look at this as a product of sines, and you could say the following. Well, of course, we know that e is equal to b times d. Alright, noticing that as well. So we can have the following. We could say that b squared times the integral from 0 to a, because that's the box. I'm talking about the x dimension first. And we have sine squared n pi x over a. This is the first component. This is going to be dx. Separately, we're going to have d squared times the integral from 0 to b of sine squared m pi times y over b dy. And you might say to yourself, well, hold up a second, how did I get these sines? Or, excuse me, sine squareds and b squareds? And I'll answer you very quickly. So if we look at just, in this case, the y component of our wave equation, the y component said the following. It was eta of y is equal to d times the sine of m pi times y over b. And in order to get a complex conjugate, you need to change all the imaginary parts, the sign of all the imaginary parts. Now, do we see any imaginary parts here? The answer is no. So what we do is we do this, so eta times of y star, that's what we mean by a complex conjugate. In this case, is going to be d times the sine of m pi times y over b. So as a result, eta of y complex conjugate multiplied by eta of y is just going to be the whole thing squared. Now, just as a matter of interest, what if I had what if I had an iota times d? What if it actually was imaginary? Well, then the complex conjugate would be negative iota. Alright, that's just to point that out. That's where we get these squares up here. Alright, I'll let you do the integration, and it's actually ridiculously straightforward. So you're going to find that the b here is equal to the square root of 2 over a, and you're going to find that d here is equal to the square root of 2 over b. And as a result, we know, of course, that e is equal to b times d. That's going to be equal to 2 over root ab. Alright, that's pretty straightforward. Now I'm going to do the longer part now if you want, and if you don't want it, just skip it. In actual fact, I see this video is pretty long, so I mightn't do the whole thing. I'll just tell you how to do it. So, doing the integral from negative infinity to positive infinity of psi star times psi dy or dx dy, that must be equal to 1. That's the condition for normalization. So I'll just set this up and I'll leave you off to do it yourself. So when you set this up, you're going to get the following. You're going to find that e squared times the double integrals from 0 to b, from 0 to a, outside of the sine squared of n pi x over a times the sine squared of m pi times y over b, and to close this, and this is integrated dx dy. If you do that, you're going to find straight out that e is equal to 2 over root ab. But to be honest, it's quite a good bit of work. If somebody wants me to do it, I absolutely will. But look, it's double integration, so it's not too difficult all the same. So let's continue on from here. And what we can say is the following. We can now say that the full wave equation, psi of x and y, well, the spatial component of the wave equation is equal to 2 over the square root of ab times the sine of n pi x over a times the sine of m pi y over b. Okay, and just remember again that we had k squared is equal to 2me over h bar squared, that negative b squared was equal to lambda squared minus k squared, lambda is equal to n pi over a, and beta is equal to m pi over a. Alright, so let's try and get our energy values here. I'll let you do the manipulations yourself. It's very straightforward stuff. And you'll find that the energy values E sub n, E sub m is equal to h bar squared outside of n pi over a to be squared plus m pi over b to be squared, all divided by 2m.